Lift was very difficult to calculate until along came a German mathematician, Kuda, and a Russian physicist, Joukowsky, who came up with something called the Kuda-Joukowsky law. This is before World War I. And it said that the lift per unit span on a wing is equal to the density of the air, the velocity of the air over the wing, and some weird thing called circulation, like this. But that weird thing makes some sense, because if you visualize a circulation of air here and you superimpose on that a translational motion of air, the combined effect is a flow like you see over the flow over a wing. And so the lift depended on the circulation. So still had to be calculated, and that was a major challenge. The next 30 or 40 years, it was something called the circulation theory of lift. Along came computational fluid dynamics in the 1970s, which allowed the calculation of the pressure distribution all over the surface. And we know physically that the lift comes from the pressure distribution exerted all over the surface. And with computational fluid dynamics, the prediction of lift in a fairly accurate way became possible. Drag, slightly different but same kind of story. The prediction of drag, the Wright brothers had no way of calculating drag. However, in 1904, Ludwig Prandtl in Germany, a very respected and well-known scientist and mathematician, came up with something called the boundary layer theory, which allowed the prediction of skin friction right along the surface of a boundary over which the flow is flowing. This boundary layer theory allowed, ultimately, over a number of years, pretty reasonable predictions of the skin friction within certain factors like turbulent and laminar boundary layers and so forth. However, there's another source of drag, pressure drag due to flow separation. This is due to the flow coming in, pinching on the front of the vehicle, separating off the back, giving you a pressure pushing the vehicle back. The calculation of that was virtually impossible. It all had to be measured in a wind tunnel until the advent of computational fluid dynamics, which again allows us now to calculate the flow field over the airplane and regions of separated flow and the pressure distribution over the surface, and again giving us a result for the pressure drag due to flow separation.
In 1927, the U.S. aeronautical industry faced a huge problem. Their aircraft, which were powered by large air-cooled engines, had a lot of drag. The engines required sufficient airflow over the cylinder heads in order to provide adequate heat removal. But the drag penalty was high. Aircraft designers knew the problem was bad, but they didn't know how bad it really was. The result of this drag penalty was a limitation in the maximum flight speeds that they could achieve. So the industry leaders turned to the National Advisory Committee on Aeronautics, or NACA, for help. Over the next few years, NACA solved this drag problem with absolutely stunning results. NACA researchers used both analytical theory and wind tunnel testing to tackle the problem. So let's take a close look at those tools. In the early days of aviation, the process of aircraft design was very ad hoc. Most aircraft inventors would intuitively try a design change, build it, and simply go up and fly the new concept. Obviously, this is not an efficient process and was even dangerous. Many daring pilots lost their lives trying out new, untested aircraft designs before much was known about flight. In fact, there's a cautionary saying in aviation. There are old pilots and there are bold pilots, but there's no such thing as an old, bold pilot. We think of test pilots as being bold and full of daring do, But in actuality, test pilots have to be very careful and methodical in their work. These days, we have 3 basic categories of prediction tools that we can use to predict the performance of a particular design: analytical prediction, wind tunnel experiments, and computational simulations. The best approach turns out to be a combination of all 3. But in the end, it isn't until actual flight test that a design is proven out, since it's the flight tests which generate critical data that is used to refine our scientific understanding and design tools. Let's start with the challenge of measuring the flow speed in a wind tunnel to illustrate some physical concepts that govern any design predictions. The pedostatic probe is an extremely useful tool for measuring flow velocity at a point within a wind tunnel. We'll talk about the theory of the pedo probe here for wind tunnels, but recognize that this is the same method used to measure the flight speed of an aircraft. It's a very simple and powerful technique. Now, the calibration of our pedo probe is based directly on the theory presented in the Bernoulli equation, which describes the trade-off between pressure and velocity. Bernoulli states that the sum of local air pressure plus the product of 1/2 times the density times the square of velocity is a constant anywhere along a streamline. To be more specific, we call the pressure term in Bernoulli the static pressure. The second term, containing velocity, must have units of pressure in order to be dimensionally consistent with the summation. We call this second term the dynamic pressure. The summation of these two, static pressure plus dynamic pressure, is called total pressure, which is always constant under the conditions where the Bernoulli equation is valid. Let's revisit the example of driving down the highway with our hand out the window. The static pressure under these conditions is equal to the local barometric pressure. The dynamic pressure is found from the air density and the speed of your vehicle. And finally, the total pressure is the sum of the two. When you extend your hand out the window of your car with your palm facing forward, the pressure that you feel on the palm of your hand is the total pressure, since the flow along a streamline comes to a rest at a stagnation point on your palm. Because the total pressure in an incompressible flow can be measured at any location where there is a stagnation point, total pressure is often also called the stagnation pressure. So, on the leading edge of an aircraft's wing, or on the nose of the aircraft, there will be a stagnation point where the total pressure can be measured. So the Bernoulli interplay between flow velocity and pressure can be restated as dynamic pressure versus static pressure. If dynamic pressure decreases and approaches zero, the static pressure increases up to the total pressure. Conversely, as dynamic pressure increases, static pressure decreases. The pitot tube, for measuring tunnel velocity, is constructed such that dynamic pressure can be found from the difference between total pressure and the static pressure, both of which can be measured. Total pressure is measured at the very front tip of the pitot probe, where the flow locally stagnates. Static pressure is measured with a manifolded array of pressure orifices around the circumference of the probe. And if we measure the static pressure and temperature of the air in this room, we can find the value of density using the ideal gas law. Then we know everything in the Bernoulli equation except for velocity, which we can now solve for. For a wind tunnel, we can connect tubing for measurements of the total pressure and the static pressure to either side of this U-tube manometer. This manometer will then measure the difference between total and static pressure, which is the dynamic pressure, by indicating a change in height of the water inside. Today, the pressure in this room is 14 psi and the temperature is a comfortable 70 degrees. If I take both of those values into the ideal gas law, I find that the density of air in this room is 0.07 pounds mass per cubic foot. I'll use this value of density of air to calculate the speed in the tunnel using the Bernoulli equation. All right, I'm now going to fire up the wind tunnel and record the test section speed using this pitot probe. First, I'll put the pitot probe into the tunnel, and I'll connect the left tube to the top, which is the measurement of total pressure. And then the right tube I'm connecting to the port coming out the side, which is the static pressure. Now when I hold the pitot probe in the tunnel and turn the tunnel on, we're going to see a change in height of the water level here. So you can see the total pressure is higher, and that's making this side of the water level go down. The static pressure is lower, so this water goes up. It's like a suction, a relative suction. I can measure the change in height, and it's 1 inch. I can convert the change in height to a pressure using the hydrostatic equation, which we discussed in the second lecture. I just need to incorporate the density of water, which we'll take as 62.4 pounds mass per cubic foot, and gravitational acceleration, which is 32.2 feet per second squared. These values give a dynamic pressure of 0.036 psi. Now, taking my value of density and solving for velocity out of the definition of dynamic pressure, we see that the test section velocity is 69 feet per second. So making only one measurement of dynamic pressure in the wind tunnel, coupled with measurement of the ambient pressure and temperature in the room to find density, I can easily find the test section velocity. Now, the Bernoulli equation is connected to Newton's second law, which states that force is equal to mass times acceleration. We can think of it in this way. A pressure difference acting across a fluid element, a small imaginary chunk of fluid called a control volume, provides a driving force on that control volume. If the pressure on the back side of the fluid element is higher than the pressure on the front, there is a positive force that pushes the fluid element forward. From Newton's second law, this push must result in a positive acceleration of the fluid, which is represented in the velocity term of the Bernoulli equation. So the result of a positive acceleration is an increase in velocity, which we see in Bernoulli. A more general expression of Newton's second law states that force is equal to the time rate of change of momentum, where momentum is the product of mass and velocity. A great way to remember the idea behind momentum is to think of a heavy truck and a scooter traveling at the same speed. A collision with a heavy truck will impart much more force than a collision with the scooter. This is because the truck has much more momentum than the scooter, even though they are traveling at the same speed, since the truck is much more massive. Conservation of momentum is at the core of the famous Navier-Stokes equations for fluid flow. This set of three equations, one for each dimension, was developed independently by Claude-Louis Navier and George Stokes in the 1800s. They describe the principle of conservation of momentum applied to fluid flow. Now let me pause here to reassure you. These equations from differential calculus are the most challenging mathematical content of the course. The main idea here is that the momentum of a fluid flow is conserved. Pressure, velocity, and viscous effects all follow this overarching rule that momentum can't be created or destroyed. And these ideas give us deep insight for analyzing fluid flows. The terms on the left-hand side are the convection terms, describing how momentum is transported throughout the domain by orderly fluid motion. The derivatives of pressure appearing on the right-hand side can be thought of as the applied force in Newton's second law. And notice the remaining terms on the right-hand side, which are pre-multiplied by the inverse of Reynolds number for viscosity. These are the diffusion terms, which describe how momentum is diffused via random molecular motion. Together with the Reynolds number, the diffusion terms describe the effects of viscosity on the flow. So any aerodynamic phenomenon can be described by the Navier-Stokes equations. Okay, so we've used the Bernoulli equation with a pitot tube to find the dynamic pressure, and then velocity in the test section of our wind tunnel. But what if we want to find the flow velocity at other inaccessible locations within our wind tunnel? For this, we'll turn to the conservation of mass. The main idea behind conservation of mass is that mass can neither be created nor destroyed. Since mass cannot materialize out of thin air, we can track mass flowing in and out of a region of interest and relate the net mass flow rate to the rate of change of mass inside our region of interest. We can apply this principle to air flowing through a system defined by a boundary. This can be either a real boundary, such as wind tunnel walls, or an imaginary boundary within an airflow that we define for convenience of analysis, such as a stream tube. Let's start with applying conservation of mass to a wind tunnel. The amount of mass flowing into the wind tunnel per unit time is equal to the density of air times the cross-sectional area of the wind tunnel times the average velocity across the cross-sectional area. We can recognize this grouping as being mass per unit time by looking at the units for each variable. Density is mass per unit volume, and the product of cross-sectional area with velocity gives volume per unit time. The entire product of density, area, and velocity is then mass per unit time. So the mass flow rate entering the tunnel must be equal to the mass flow rate leaving the tunnel, since we don't have any change of mass within the wind tunnel. Recall that mass can neither be created nor destroyed. This directly leads to a very helpful equation in aerodynamics, where the product of density, cross-sectional area, and velocity is a constant at any point within a wind tunnel. This explains why the velocity goes up when the cross-sectional area goes down. Think back to the garden hose example that we discussed in the lecture on lift. When the exit area is decreased, the velocity at the nozzle of the hose must go up. This is the exact same reason why our wind tunnel has a decreasing area duct. The wind tunnel is drawing in air at low speed from the room and accelerating the air to a higher velocity in the test section. With our wind tunnel here, for example, the test section area is 36 square inches, and we just measured the airspeed in the test section at 69 feet per second. What if we want to find the velocity up here, ahead of the contraction? Based on the conservation of mass, we know that it's going to be lower, since the cross-sectional area is higher. Since the upstream area is 256 square inches, or 7.1 times larger, the flow velocity here is 7.1 times lower, or a mere 9.7 feet per second. That's such a low speed that I really don't feel any breeze at all ahead of the wind tunnel, even when the test section speed is 69 feet per second. Likewise, if we need to know the local velocity at any other point within the wind tunnel, all we need is the local cross-sectional area. Now let's turn to the third and final physical principle that governs aerodynamics. Conservation of energy follows the same theme as the previous two conservation concepts that we discussed. In this case, the principle states that energy cannot be created, nor can it be destroyed. One important relationship uniquely resulting from the conservation of energy is the so-called energy equation. Before discussing the energy equation, we need to define one important parameter, the specific heat, which is abbreviated CP. It's basically a measure of the heat carrying capacity of air and is a constant property of air over a wide range of conditions. Let's now turn to the energy equation. It actually has a form very similar to the Bernoulli equation, but relates the flow velocity to temperature instead of pressure. The energy equation states that the product of 1/2 times the square of the velocity plus Cp times the temperature is a constant. The value of this constant is referred to as the total temperature, or the stagnation temperature. The idea behind the definition of total temperature is the same as that for total pressure. Here, the energy equation describes a trade-off between the flow velocity and temperature. The velocity can be thought of as kinetic energy, while the product of Cp and T can be thought of as a measure of the internal energy of the fluid. As the flow's kinetic energy increases, meaning an increase in velocity, the internal energy decreases, which is a measure of a drop in local temperature. If we have air starting at room temperature and then flowing through a wind tunnel, as we accelerate the flow, the kinetic energy of the air is increasing. If there are no other heat transfer mechanisms present, the flow temperature must decrease. But there's another way of looking at the energy equation. If we place ourselves in the frame of reference of an aircraft traveling at high speed, the airflow relative to the aircraft has a temperature equal to the ambient temperature and a very high kinetic energy due to the high flight speed. As that high-speed flow approaches the stagnation point on the leading edge of the wing, it decelerates. Based on the energy equation, the temperature of the decelerating flow must increase. Thus, when the flow reaches the leading edge and completely stagnates, the temperature reaches the stagnation temperature, which can be quite hot. This is actually a limiting factor for high-speed flight. High-speed aircraft such as the SR-71 Blackbird had to be made from special materials in order to sustain the high heat loading on the leading edges due to the high stagnation temperatures associated with high-speed flight. So let's pause for an interim summary. We showed how the conservation principles are based on the central idea that key quantities, mass, momentum, or energy, can't be created nor can they be destroyed. We developed these physical concepts into equations by applying them to a control volume, with quantities flowing in and out of the control volume. In the process, we developed some very useful equations, such as the Bernoulli equation or the energy equation. It's important to recognize, however, when simplifying assumptions are used to develop some equations. For example, the Bernoulli equation is predicated on the assumption of an incompressible flow, basically neglecting any changes in density. If indeed the changes in density are appreciable, then the Bernoulli equation will lead to errors in the analysis. Flows generally have compressibility effects appear when the Mach number increases above about 3/10 of the speed of sound. In those higher speed conditions, we have to rely on other theories and equations to analyze problems. So with compressible flows, we generally rely on theory developed from the conservation of energy. So let's now move on to a discussion of the tools available for studying aerodynamic flows. We have analysis, wind tunnels, and numerical simulation. Analytical tools were some of the earliest approaches used to estimate the lift produced by an aircraft. Analysis offers the advantages that no specialized equipment is needed to come up with an estimate, and they are simpler to perform than most computations. However, there are a number of simplifying assumptions that must be made in order to describe the flow. Essentially, we model the flow in a certain way and apply the physical principles that we just described. In a few very limited cases, the theory exactly describes what we would find in nature. For example, the flow through a confined channel with a moving wall is a case where we can apply suitable boundary conditions to the nonlinear Navier-Stokes equations of fluid flow in order to come up with an accurate description of the flow behavior. One analytical tool was developed in the early 1900s by researchers in Germany. Led by a distinguished scientist named Ludwig Prandtl, they came up with a description of lift based on a bound vortex on the wing, called lifting line theory. They basically came up with a way to model the induced downwash of the flow over the wing and the strength of the tip vortices. Imagine a horseshoe-shaped vortex filament extending along the span of the wing and trailing from each wingtip and extending downstream to infinity. This seemingly esoteric construct was actually extremely successful in describing the amount of lift generated by a wing and is still used today for first-order analysis. In the 1930s, a bright scientist named Theodor Theodorson, working for NACA's Langley Memorial Aeronautical Lab, developed a technique for predicting the pressure distribution and lift on any airfoil, knowing only a description of the geometry. This was a huge leap in capability at the time, since it now allowed designers to reliably predict the performance of an airfoil without resorting to cut and try techniques. Now, while accurate analytical tools have been successful in predicting lift, there are a huge number of assumptions that must be made, and these are always a limitation of a purely analytical approach. So from the early days of aeronautical engineering, careful experimentation has been a hallmark of engineering practice. The earliest attempts at creating experimental facilities for aerodynamic testing were focused on the development of a whirling arm. It was relatively straightforward to mount a model on a whirling arm, spin it around, and measure the amount of lift. In many cases, the technique was to indirectly measure the amount of deflection of the arm in the vertical direction. For example, Samuel Langley was one of the first experimentalists to develop such devices in the late 1800s. The key disadvantage of the whirling arm, however, is that the model passes through its own wake, leading to disturbed flow that alters the measured forces. This limitation led to dissatisfaction with the whirling arm concept and ultimately led aeronautical engineers to develop wind tunnels. The Wright brothers were actually some of the first engineers to develop and use a wind tunnel in a systematic manner for their design work. The main idea of a wind tunnel is that it uses some energy source, such as a fan, connected to a motor to accelerate the flow through a channel. The area of the wind tunnel varies throughout in order to accelerate the flow. And by conservation of mass, flow speed goes up when the cross-sectional area goes down. The test section will be the point of lowest area, so the airspeed there can be the highest. And downstream of the test section, a diffuser with gradually expanding area is used to efficiently decelerate the flow before exhausting it into the room. Now, when I was a kid in the 3rd grade, I was passionate about aerodynamics and inspired to build my own rudimentary wind tunnel in the same vein as the Wright brothers. The only problem was that I didn't know what I was doing. I attempted to build a wind tunnel out of a fan and a cardboard box. I hung my best paper airplane design in the wind tunnel and was excited at the thought of watching it rise to the top of the tunnel by the lifting action of air flowing over the wing. However, all that I observed was the paper airplane just whirling around in circles. It turns out that the chaotic motion of the paper airplane is due to the swirling flow from the fan. The way to counteract this is to use flow straightening elements to remove the swirl. Wind tunnel designers routinely use a honeycomb material for this purpose, which breaks the flow up into small segments and causes the transverse components of the velocity to dissipate. Coming back to the Wright brothers, they used their own thoughtfully designed wind tunnel to test various airfoil shapes that they were considering at the time. Their wind tunnel had two big limitations, though. It was limited to two-dimensional airfoil shapes mounted between the two end walls, and it was a low Reynolds number tunnel. The 2D limitations were overcome by Gustave Eiffel, the same Eiffel who was the designer of the famous tower in Paris. Eiffel built a much larger wind tunnel in 1912, which afforded sufficient space in the test section to accommodate full 3D models to be tested. This provided insight into the three-dimensional aspects of aerodynamic performance. Amazingly, Eiffel's wind tunnel remains standing and in operation today as the oldest functioning aeronautical laboratory in the world. The second limitation is common to both the Wright's wind tunnel and to Eiffel's. Both were low-speed, relatively small-scale wind tunnels where the Reynolds number was very low, which denotes that viscous effects were large. It turns out that thin airfoils perform much better than thick airfoils at low Reynolds number due to flow separation characteristics. But at aircraft scales, a thicker airfoil is a much better choice. So interestingly, the use of small wind tunnels drove the design of airplanes in an off-optimum direction due to the limitation of the earliest wind tunnels. Initial aircraft designs relied upon thin wings, while a much better solution would have been thick wings. It wasn't until 1923 when the National Advisory Committee on Aeronautics commissioned a special purpose wind tunnel at Langley Aeronautical Lab in Virginia that researchers could replicate the Reynolds number encountered in flight for aircraft of that time. They tested hundreds of these airfoil shapes and gradually built up an understanding of the impact of various design parameters on the lift production. Wind tunnel types include open return facilities, such as this one, which draw in air and exhaust it. Other designs actually close the loop, returning the exhaust flow back to the entrance in an effort to reduce the overall energy cost of the system. The size of wind tunnels can range from the very small, such as the Wright brothers design, to extremely large wind tunnels. In fact, the largest wind tunnel in the world can fit an entire Boeing 737 inside the test section. The National Full-Scale Aerodynamics Complex at NASA Ames Research Center has a test section that measures 80 feet high by 120 feet wide, with 72 megawatts of power required to keep the air flowing through the facility. That's enough electricity to power a typical community of about 60,000 residential homes. One of the key challenges with wind tunnels is to emulate the physics of flight as faithfully as possible. However, there are some physical limitations that are sometimes insurmountable. For example, viscous effects are one of the most challenging aspects of the physics to get correct in a wind tunnel. The transition between laminar and turbulent flow is notoriously difficult to get right in a wind tunnel. Reynolds number, which indicates the relative significance of viscous effects, is a helpful parameter here. Aerodynamicists attempt to match the Reynolds number in a wind tunnel environment to what is encountered in flight, but problems such as the turbulence intensity level of wind tunnels are still difficult to overcome. Wind tunnel experiments are also faced with the challenge of high cost, particularly for large-scale testing. Even the NASA Ames Research Center can't accommodate the largest commercial aircraft and can't match cruise speeds of commercial airliners. The third approach to predicting the aerodynamic characteristics of a flight vehicle involves numerical simulation. There are a number of approaches available to researchers and engineers with varying levels of fidelity. Most often, there's a trade-off between computational cost, measured in time or CPU hours, and the fidelity of the simulation. First-order simulations of the flight vehicle aerodynamics can be done on modern computers in the blink of an eye. These simplest tools are very closely related to Prandtl's lifting line theory, described a few minutes ago, with the computer solving the flow field resulting from a large system of bound vortices. These methods are called panel codes, where the flight vehicle's surface is segmented into panels, with each panel having a bound vortex associated with it. These quick solutions are incredibly useful in the design cycle, where new ideas and concepts need to be assessed quickly and in an iterative manner. However, fast tools such as panel codes are not very useful for tricky aerodynamic situations such as predicting flow transition or separation. When more fidelity is needed, designers can use computational fluid dynamics, commonly known as CFD. The basis of CFD is numerical simulation of the three conservation equations, which are coupled using the ideal gas law as a closure equation to make the system of equations tractable. The solution domain represents the area of flow around the flight vehicle and is broken up into a huge number of grid points. At each grid point, and for each time step in the solution, all of the conservation equations are solved simultaneously. So, in summary, aircraft designers have three approaches available to predict how an aircraft will perform: analysis, experiments, and computations. And all three of these tools are based on the fundamental concepts of conservation of mass, momentum, and energy. Each one of our design tools has distinct advantages and limitations, so the most successful approaches to aircraft development involve all three of these tools working in conjunction to deliver analytical predictions of aircraft aerodynamics. And the designer uses these tools and principles to determine the aerodynamic loads on the aircraft, lift and drag. These loads dictate performance and structural requirements. Let's now come back to our opening story on the drag resulting from air cooling of radial engines. NACA had built the Propeller research tunnel specifically to study questions like this one. So NACA researchers immediately went to work pursuing a systematic study of various cowlings that could be used to optimally direct the airflow around the cylinders. After just about 1 year of effort, they came up with some stunning results. They found a 59% reduction in drag with one of their cowling designs. A few years following the wind tunnel studies, the bright theoretician Theodorson provided an analytical standpoint for the low drag performance of the NACA cowling. Spurred on by these amazing results, NACA installed the cowling on a Curtiss AT-5A and performed flight tests. These results were equally stunning. Whereas the AT-5A in its baseline configuration had a top speed of 118 miles per hour, with the new NACA cowling, they hit a top speed of 137 miles per hour, a 16% increase in max speed. And on top of that, there was absolutely no change in the cooling of the engine, as the oil temperatures remained the same. This huge jump in performance led industry to immediately snatch up the NACA cowling concept, with the Lockheed Vega being the first aircraft to install the cowling. The Vega turned out to be one of the most popular aircraft of the 1930s, flown by Wiley Post and Amelia Earhart. And NACA's achievement won them the Collier Trophy in 1929, which is awarded for the most important achievement in American aviation. This is the story again and again. Wind tunnels and analysis, later aided by computational modeling on computers, are what have made possible the rapid development of aviation over the past century.